I hope that you learned from your assignment of the first video and have got some feeling now that the choice of materials does really matter in the design of products. Now we will go further with the explanation on the LCA calculations and tools. Be aware that some slides and explanations are a bit more complex now. When you don't understand, just stop this video and play the difficult part again. So far, we learned that LCA is a matter of calculating the mass and energy balances of a system that produces a product or service as output. The input are resources like materials, electricity, water, and chemicals. The LCA practitioner should define the system and quantify the energy and raw material inputs. The result of the calculations must be the list of emissions like carbon dioxide, methane, nitrogen oxides in air, heavy metals in the ground, and nitrate and phosphate in water. The problem is now, we need a comprehensive list of emissions to air, soil, and water to assess the impacts. How to obtain this? The answer is, we have databases that provide these data for many processes. The way we solve the problem is looking at the structure of our system in more detail. We distinguish in upstream processes of the supplies, also called background systems, the core processes under study, also called foreground systems, downstream processes, often a mix of foreground and background systems, and in between there is transport. The LCA practitioner must collect the supplies as well as the emissions from the foreground process. However, it is not doable to collect the emission data from all background processes of all supplies, such as metals, chemicals, and plastics. The same applies to all downstream processes. The issue of the emissions of background systems is solved by big databases with lifecycle inventory emission data. These databases comprise several thousands of processes, of which the average emissions are known. There are data on mining, transport, electricity, heat, production of plastics and chemicals, waste handling and recycling processes, and many other materials like wood, bamboo, and ceramics. These databases are from EcoInvent, Gabi, AgriFootprint, TU Delft, and many others. In this course, we will apply the Innomat database of the Delft University of Technology. For the foreground systems, a different kind of databases is required that combines the many emissions into so-called midpoint groups and endpoint indicators. This is done on the basis of the relative importance in terms of toxicity and scarcity. I will come to that a few slides later. But how did EcoInvent, Gabi, and AgriFootprint create their big lifecycle inventory databases for more than several thousand processes? We will have a look at it by means of an example. It is about a sheep in a trailer that goes to a slaughterhouse at the moment the truck leaves the gate of the farm. The breeding of these sheep generate far more than 500 emissions to the air, as we call it from cradle to gate. It might be that you think, how on earth do they arrive at such a list? Well, the assembly of such a list is done by means of computer software in a clever way. That is done as follows, by the so-called tree. This tree is a pyramid of sub-processes that add up to a total. On top of the tree you have the sheep. To breed the sheep, you need products and its subproducts. You need soybeans plus maize for food. You need fertilizer for the land. You need a shed for the sheep. And you need a lot of transport. And each product has its subproducts and subprocesses. Let's look at a shed. What kind of products do you need for a shed? It are the blocks in blue. To build a shed, you need concrete for the floor, steel beams for the structure, wooden cladding for the walls and a roof, and of course transport. For transport, we need diesel oil and a truck. For a truck, we need steel. For the steel, a factory. And for the factory, we need to transport steel. So the tree is endless, and computers can solve that problem. However, when we do such a calculation by Excel, then we stop at the level that the blocks have less pollution than 1 to 2% of the total. You can imagine now that you can build a lot of cradle-to-gate processes with much less basic building blocks. With 500 to 1,000 basic sub-processes, you can easily build a 10-fold of lifecycle inventory lists of other products, assembled from these basic inventory lists. You need a computer for that. And you will need to assemble what hundreds of scientists all over the world published on detailed LCA studies. Another example is the LCA of 1 kilogram of steel. It shows an inventory list of more than 700 emissions. The problem is now how to address all these emissions. Which ones are important? How do we decide which ones to use when comparing products? To resolve this issue, we need Lifecycle Impact Assessment, or LCIA, which is the next step in LCA. The solution is that we need a single indicator to compare alternatives for example, a pair of jeans at the start of this course, or compare sheep of different farms, or steel of different factories. And you can imagine, there is more than one way to create such a single indicator. Basically, there are 3 types of single indicators. The first indicator we deal with is the carbon footprint. It is in a way the easiest route to a single indicator. You simply throw away the whole list except from carbon dioxide. It is easy to understand what you do. You have then a so-called single issue score on the important issue of global warming. The second possibility is to try to calculate the external damage of each emission and add it up to determine the total damage. Such an indicator is the recipe indicator system, providing the damage information in points. Damage is nice to know, but hard to calculate, so not accurate at all. The third solution is that you do not look at the damage, but that you look at the cost to prevent that damage. You reduce then the emissions to a no effect level that brings nature of our Mother Earth in equilibrium again. Such a system is called prevention-based and is monetized, so expressed in euros. The eco-cost system is such a prevention-based model. We apply that in this course since it's the most applied monetized indicator in science and it is easy to understand for business people. This slide shows the calculation structure that is applied to arrive at indicator scores. The first calculation step is called classification and characterization. First, you combine the emissions in groups called impact categories that cause the same physical, chemical, or medical effect. For instance, all substances with a greenhouse effect, such as carbon dioxide and methane, go into the impact category that cause climate change. Other substances go into groups that affect the ozone layer, human toxicity, ecotoxicity, etc. Within each group, you know the relative effect of each substance, called the characterization factor. For instance, methane is about 30 times more harmful than carbon dioxide. Or for short, 1 kilogram of methane equals 30 kilogram equivalent carbon dioxide. In such a way, you can calculate the score for each impact category, also called midpoint. But we still have to go to a single indicator. We will convert the midpoint groups into 3 so-called areas of protection. 1 for human health, 1 for natural environment, and 1 for resources. So we have to combine the damage of the depletion of the ozone layer, carcinogens, and respiratory diseases to end up with the endpoint for human health. The same principle applies to the endpoints of natural environment and resources. These calculations are very sophisticated, very complex, and are based on many assumptions. The result is that endpoint calculations are rather inaccurate compared to the midpoint calculations. Some systems regard global warming as a fourth area of protection, since it's hardly possible to calculate the impact of greenhouse gases on the three aforementioned areas of protection. And still the last issue has to be resolved. How important are human beings compared to our nature? Of course, this last weighing step is subjective, but most LCA practitioners apply 0.4 as multiplier for human health and ecosystems and 0.2 for resources. Then you end up with your single score. Quite arbitrary, but there is no other possibility in damage-based systems. In monetized systems like eco-costs, it works a bit different. Each midpoint has its own marginal prevention costs. Once all midpoint indicators are converted to euros, they can be added up to an endpoint and from there to a single indicator. ISO 14008 defines the requirements of monetization of midpoints. There is an ongoing debate on the issue of using midpoint indicators versus endpoints. The advantage of midpoints is that they have a more direct relationship with effects, and therefore seem to be more accurate. However, it is a misunderstanding that midpoints are accurate in the sense that no subjective assumptions are taken. An example is the characterization factors of greenhouse gases. When you take 100 years as calculation period for global warming, methane has a factor of about 28 to 34. When you take 500 years period, the factor is 7 to 8. And when you take 20 years, the factor is 84 to 96. So the global factor you take is a matter of the subjective choice of the number of years in our global warming calculation. The effect of sulfur dioxide emissions differ in Europe per country, and the factors for human toxicity have a huge uncertainty of more than a factor 100. But the main argument to take midpoints, however, is that it is wrong to combine apples with oranges. The disadvantage is that there are many midpoints, so which midpoint should be taken as a leading in LCA benchmarking? Which midpoint is more important than the other? The story of Volkswagen Diesel reveals how dangerous it is to base your corporate strategy on carbon footprint only. They became champion in terms of carbon dioxide emissions, but ignored other emissions like NOx at a corporate cost of several billion euros. So the advantage of midpoints is that many effects are shown with lower uncertainty than endpoints, but the disadvantage is the difficulty in interpretation of the whole dataset in terms of product benchmarking. The disadvantage of endpoints is a higher uncertainty with more subjective assumptions, but the advantage is easier interpretation of your product comparisons. Contrary to what many environmentalists think by their instinct, the uncertainty of damage points is much higher than the uncertainty of monetized systems based on prevention costs. In a practice, a factor 50 versus a factor 2. I already mentioned the uncertainty in the toxicity list. These lists are extremely important, however, at the same time hard to calculate. This slide gives you an impression of the damage calculation. We start with the emissions to nature that will end up in our food. When we eat it, we might get ill. In serious cases, you end up in a hospital. Such an illness is weighed in terms of a DALY, a disability-adjusted life year. When people die and lose, for instance, 10 life years, the DALY is 10. There are tables for the DALY of the World Health Organization for people who have a non-mortal illness. I can imagine that such kind of calculations are strange to you, but when you look at the details, this DALI system seems to be as such quite objective. But the pathway from emissions to illness is the real problem in terms of uncertainties. Now I will make it a bit more practical. There are tables of the results of the calculation. This slide shows a part of the midpoint table of the IPCC on greenhouse gases. You see in this table that methane of fossil origin contributes 30.5 more to global warming than carbon dioxide. You see also the eco-cost of fossil methane is 3.54. You see as well that biogenic methane, which is methane from fermentation, has eco-cost of 3.22, which is a bit lower because of its natural life cycle in the biosphere. This table contains also data for chemicals that are toxic to humans and to ecosystems and comprises more than 36,000 substances in air, water and soil. That is really a lot, but there are still substances of which the toxicity is not known yet. What you need in practice as well is the eco-burden of the background processes. We will work in this course with the Innomat App 2020 tables containing more than 1200 LCAs of industrial products and processes. An additional table shows approximately 1000 LCAs of agriculture from agri-footprint. The slide shows some calculation results for non-ferro metals. €184 per kilogram eco-cost of the trade mix of aluminium. The trade mix is the average global mix of virgin and secondary materials that can be found in the products of that metal, like pipes and beams. Other results are €5.08 per kilogram for copper wire and €624.81 per kilogram virgin silver. This Excel file also contains data for other materials like plastics, textile, wood and fuels, as well as for heat, electricity and transport. Background data for processes like welding and coating have been calculated as well. At the end of the table there are data for end-of-life processes like combustion with heat recovery, recycling, composting and landfill. This slide shows how to make calculations with the help of previous Excel tables. The example is on your second assignment, an LCA of a felt tip pen, materials only, step 1, hotspot analysis. The easiest way to structure such a calculation in an Excel worksheet is to make a list of components in the first column, give the weight in kilograms in the second column, or megajoule for energy and ton times kilometers for transport. Provide additional info like the type of material in the third column. Copy the data lines that you need from the Innomat 2020 file and paste it in your Excel sheet. Then copy and paste the database line number and the eco-cost per kilogram in the columns next to the column with the additional info. Multiply the weight of the second column to the eco-cost per kilogram of the fifth column and give the result in the sixth column. Calculate the sum of the sixth column, which is the total eco-cost score of the calculation. What we see here is that the hotspot is the aluminium body of 4 kilograms per 1000 felt tip pens, for the case that the end-of-life scenario has not been decided yet. This slide shows what we can do about the hotspot. I reduced the LCA benchmarking now to the material for the body of the felt tip pen, since that is the only thing that will be changed in the comparison. Look at the materials, the extrusion and the end of life of the material, under the assumption that the pen is either burned with heat recovery in a municipal waste incinerator or taken back by the manufacturer and recycled. The analysis shows that the body of bio-PE is better in the scenario that the pen is incinerated, but the score is better when the manufacturer takes the pen back for recycling, the so-called closed-loop recycling, because of the recycling credit in LCA. Note that fossil plastics score much worse than bio-PE. The reason of it is explained in the third block of this first lecture module, which is on end-of-life and cradle-to-cradle modeling in LCA. You are asked now to do your second assignment, the analysis of the felt tip pin. With this assignment, I wish you a very fine learning experience.